Hello and welcome to week 14. This is probably one of my favorite topics to teach. I do speaking events on AI, generative AI, and LLM. I've taught classes just on this. I teach this at work. This is by far probably one of my favorite topics. Regretfully, I only have maybe an hour to go into this, and it's not going to be that long, so I want to show some demos tonight or tomorrow. But this is probably one of the most impactful things that you can learn is what is AI, how to use AI, things like that. Now I'm going to cover a little bit. The way I structured this outline was a little different than I've ever done it before. I took parts of every one of my lectures and added a few random slides. If you find something you're interested in, Google it, dive deeper, because there's no way I'm going to be able to give you enough depth to really understand this. But this will be a lot of the future in the next 5, 10, 15 years. So let's get started. Okay, so I wish I could have taught this in the really beginning, but the way we kind of have to teach computers is we teach you kind of, and this was like sort of from another course, but basically, Excel, SQL, how the data stored. You got to really kind of understand the data, the Excel, the variables, how to do an average. You got to see some of that stuff. That's seeing the data, verifying the data, basic analytics. So this is what you've been doing almost all semester. Is these two things here? Maybe not. They might have different work. But this is literally all you've been doing. Say using Python, you use Excel. Big whoop, no difference. It's still a program that you can see the data, you can verify the data, you can run basic analytics. Well, this is what you've been basically doing the whole semester. ETL, you open up an Excel workbook, you do some changes to it, and then you send it off to your boss. At the end of the day, that's really ETL. Now we're here, and we're going to cover just real basic machine learning, unsupervised and supervised CNN RNN. Normally, this is a 3 or 4 week lecture, so I'm going to really try to condense it down. But even after this, and the next thing you need to learn is how to apply it. And we have access to ChatGPT, but am I really using ChatGPT the best way? And that's decision support. So if I was to ask you a question, and you have the money, but how much would you pay to make $20 million? That's a fair question. If I could pretty much guarantee you'd make $20 million. I had a stock or I had some type of tool or I had a money press, and you can make $20 million a year. How much would you pay to make $20 million a year? Well, you definitely pay $1 million. And give $1 million away, you get 19 back. It's a no-brainer. 5 or 10 is probably a no-brainer either. So now why do I ask this? Because this is the way good companies look at AI engineers. If an AI engineer can save $20 million a year and it only costs us $500,000 to hire them, that's a smoking deal. On the first day or two, or I can tell you the first week of my current position, I I found a little thing using word to vec using a little basic machine learning. And I think I saved $60,000 or $80,000 within the first 2 days of me working there. I mean, and that was a month. Well, let's say that was 6 months ago. Just imagine how much I've saved the company now. I mean, and really, in the last 6 months, I've saved the company, I know, over $1 million. So that easily pays for my salary and my boss's salary and some of my coworkers' salary. So, when you think about machine learning, this is where the drive is. Yeah, if we can find ways to save X amount of money, $100 million a year, that's only going to cost us, a million or $10 million. It's a no-brainer for companies. It's a no-brainer. So just keep that in mind. That's where the driving economics is behind it. And here's an example, though. So antibiotics, vancomycin, there's a ton of them, erythromycin. They're antibiotics that basically get rid of bacterial infections in your body. Um, Now, there's something called gram-positive, and gram-positive can just be generally a more resistant or stronger bacteria. I guess the easiest way to say it. Okay. What's really interesting is that there are basically no new antibiotics classes, I guess, discovered in a long time, since I don't know, 20, 30 years. And so um, antibiotics are important. Antibiotics are a huge market. They're a $50 billion US market alone, $50 billion in the US alone. And there hasn't been a lot of movement in that sector. It's been kind of stalled. Well, they used machine learning and they discovered a new class of antibiotics, not a new antibiotic, a new class of antibiotics. I mean, that discovery alone is $1 billion discovery. It's easily $1 billion discovery. And so AI basically on this method walked the researchers through how it found the new class, what it did, how to duplicate it in the lab, how to do everything. And so far, it looks very promising. So, I mean, machine learning had discovered a new class of antibiotics in a $50 billion market. Even if it only makes a small dent, it takes 2 or 3 billion. That's still a huge profit. Oops, let me go back. Sorry about that. Um, this is a paper, and I included a QR code to use this for different presentation. This had to do with how people interact with chatbots. Are they inherently happy to deal with a chatbot when they don't necessarily know it's a chatbot, or they rather deal with a doctor with things like this? And from what I remember, I need to reread this too, but from what I remember, people generally like to deal with chatbots on user forums and the internet because a chatbot can give a longer, more detailed description. Where physicians tend to be a little short worded, like everyone. When we're all busy, a physician or a doctor just has to type something out and move on. They don't have time to really reply to long-winded responses on the internet. However, a chatbot, that's no big deal. So people even like to deal with chatbots as long as there's accuracy and other things. Here's here's one of my favorites. So I say the brain, I say neuroscience, one of the true things I really love. And there's a bunch of different ideas that we all see the world differently. We all dream differently. If I see something on TV and you see something on TV, we might see it in our mind differently. So how do we interpret that? How do we know if that's true? How do we interrogate that? How do we know what you're thinking? Well, there's more research coming out nowadays where we basically hook a patient up to a machine that can read your electrical signals. We run it through, I believe this was through a GAN or through a diffusion generator, a diffusion model. And like, hey, look, here's what we show them. And this is what subject one saw, and this is what subject two saw, what subject three or five, whatever saw. So now we're really starting to say, hey, this is what you see, and this is what your mind saw, which is really interesting, being able to read people's dreams. And just in the terms of policing and forensic and other things, I mean, when a cop says he saw a gun, we don't know if he's telling the truth or he's fibbing. But now with techniques like this, in a few years, we'll maybe be able to know. Do you have night terrors? What are your night terrors up? Let's record a couple nights of your nightmares and see what's going on. Did that movie set off a trigger point for you? Why? Let's figure these out. So it's really, really fascinating what machine learning is doing. So um, again, like I said, this is a collection of just different talks, notes, PowerPoints I've given over the years. That's why the numbering and the formatting is all weird. But we have generalized artificial intelligence or just artificial intelligence. You guys did linear regression in Excel. That's artificial intelligence. I call it, not really intelligent, just a simple AI checker. Okay. Um, and like I said, that might just be a simple system check, linear regression, something very simple. Then we move kind of down, we tighten it up a little bit more. We want to look at, if you have something, what's your risk? What are we predicting? What are we seeing in the future? Okay. So that's where kind of more machine learning is. So, if we look at stocks and we just simply backwards, or we do some simple linear regression, yeah, that's artificial intelligence, but it's not really intelligence. But if we take that same stock data and we run it through some type of, Darren or LTSM, some type of machine learning model, and we start looking forward, that's more traditional machine learning. And everyone has slightly different definitions, and that's fine. Now, deep learning, okay, let me see if I can get on camera. Deep learning is more pattern finding, and maybe, you know, pattern finding is probably one of the best ways to define it, but it is looking for patterns that we might not be able to readily detect. So, um, it's a more advanced, or it's a brain-like thing that we kind of train to look for patterns, circles, lines, edges, repeating patterns, things like this. Finally, we have generative AI. And this is where the big boom has been lately. But generative AI is more than just looking at the future. It's more than just trying to find patterns. It is, you know, making new information, it's making new data. It's taking what we were trained on and making new data, assembling that data in a way that makes sense and is coherent to us. So that's kind of the breakdown of artificial intelligence, machine learning, and generative AI. Again, these terms we kind of sometimes use interchangeably, and sometimes they're perturbed. But just to give you an idea of what they are, that's a basic overview. You know, and it's funny 'cause I don't talk about this a lot, but one of the, and this is normally explained with rules, but this is a little bit nicer image I like. When we think about machine learning, we're not trying to explain every rule. We're not trying to explain every problem. We're giving the computer data and asking it to basically make a model, make a program. So let me explain traditional programming. I'm sure a lot of programmers are going to get upset about this, but whatever. Um, we have a program and we have data. This program processes the data in some type of structural or rule-based method. Program basically processes the data in structured or rule-based method. Then we get the output. So, it's our job as a programmer to basically define the rules. And that would be, hey, how do we go into the house? Well, first we walk up to the door, we find the key, we unlock the door, we twist, we define all these steps. And sometimes there can be hundreds of steps, thousands of steps, sometimes there's very few. Well, with machine learning, we kind of take a different approach. We have a bunch of videos of people going into the door, and we let the computer basically write the set of rules, saying, hey, here is videos of a person going in the door. I want to go in the door, make some rules for that. And that's more kind of how we learn as humans, to be honest with you. We observe people's output, we mix it with real world environmental data, and we kind of come up with our morals, our consciousness, everything. So this is how kind of machine learning works. And, like I said, you can kind of see it here. It makes a lot of sense in this graph, but it does get blurry down the road. Deep learning, this is an odd slide I put here. But deep learning is just it's a subset of machine learning that is kind of inspired by our brain. It uses the same building blocks of the brain. Instead of using a wet neuron or a biological neuron, it uses silico or a virtual neuron as weights and balances. And we basically just cut down a problem to logical ones and zeros, and then we add weights, and then we say, hey, here's a bias or the weight, boom, what's our end output? Let me show you what this looks like a little differently. For those of you who've taken biology or any biology class or neural class, this is a neuron. It's a biological neuron. You just go to Wikipedia, neuron, and we get a signal that goes in here, so multiple signals, and that repeats the signal down. Well, guess what? This is exactly what an artificial neuron does. It takes input from different sources. It does some type of transfer function, Then, and that could be a summarization. That could be, I mean, it could be all different types of things. And it passes it forward. It says, "Hey, go to this another neuron, or don't go to this another neuron." Here's what a little bit more complex one looks like. And I have this other slide too. I'll let you just think about that for a while. This bottom left one, I think I got right out of my biology book. And I think this was the same size before. I think this one I got from one of my intro to neuroscience classes as an undergrad. Um, and then we have this, a very, very similar thing. So they're based on biological neurons. So they're not really that different from us in terms of the way they're structured, the way they learn. Then from there, there's something called a Hebb's postulate. Hebb's postulate in medicine and neuroscience is very simple. It says that neurons that fire together wire together. And what do I mean by that? To reinforce a habit, we have to do over and over again until it becomes a habit. To do something, to get good at something, you have to do it over and over again until it becomes muscle memory. We do it over and over again so we can strengthen pathways in our brain. Well, what's that called on a computer? That's called training. When you train a model, what are we doing? We're doing it over and over and over again, strengthening these pathways, strengthening these pathways. We're weakening other ones and strengthening these. So, well, I'm gonna skip this one. So I guess remove it. So now, really, there's two major divisions of, I guess, machine learning, probably more, but there's so much actually, but there's so much supervised. So there's unsupervised data. Unsupervised learning, unsupervised machine learning is supervised learning. Unsupervised learning involves working with data sets with no labels. So we don't know, if we're looking at a bunch of rows and columns, we don't know what one is disease and what one's not disease. It is a data set that we don't know really, that we don't know what's labeled and what's not labeled. When we go into a relationship, we don't know if it's going to work or not work out. It's an unlabeled event. Okay. There's a lot of things that we do. We don't know if, we don't know if there's labels on it. And so there's very limited things. There's limited things we can do with that. We can cluster things together. We can, do decision trees. So there's a lot of things we can kind of do, but it's still limited on what we can actually do. And clustering is generally the number one probably thing we do. And then the goal is to uncover, if we do clustering, what else is around that output that might be in alliance with that. So if I'm looking at target sales data, okay, and I say, hey, this type of shopper spends more money in December, what are other customers that are like him? And so that's kind of a real basic clustering. And where supervised learning, you have very clear data. This person has Parkinson's. This person does this. This is a picture of a cat. This is a picture of a dog. This is a person who has a fraudulent transaction. This is a person who does not have a fraudulent transaction. That is labeled data. And then when we have labeled data, we train that kind of on the data we have, which is nice, but it's really not valuable. But we hope that the training that we use applies to new data. Maybe most of you know how to drive a car. Let's say you know how to drive a Chevy truck. If I put you in a Ford truck, hopefully most of you would be able to drive it. It might take you a while, and you might not be great at first take. Maybe the buttons are weird or whatever. But at the end of the day, you can drive a Chevy. You should be able to kind of drive a Ford. You should be able to do new events based on your past training. And that's a lot of what supervised learning, machine learning is. We train it on the data we have, and we get more data. We see what it outputs as a result. Um, there's also, and this is more in LLMs. Okay, these are just more terms I kind of want you to know. Zero-shot learning allows an AI system to recognize a new concept without examples, like a robot generalizing new objects. Okay, so maybe it knows what an apple is, but doesn't know what an orange is. So it says, hey, it's like an apple, about the same size as an apple. I buy it in the supermarket like an apple, but it's a different color. So I think it might be something like an apple, but with a different color and different name. Few-shot learning is where you give the machine model, a machine learning model, or an LLM, an example of what we're trying to do. So normally when we train a machine learning model, we have to give it thousands of examples, okay? So an example would be like this Ford Chevy truck. We spend, I don't know, 5 years driving a Chevy, and hey, look, I'm good at this, Heartbeat of America, whatever. I'm good at driving my Chevy truck, which I don't have. And then I switched to a Ford. After a couple times, I can drive it pretty well. Oh, I move over to a Dodge, I can drive that pretty well too. They're all slightly different. I might not be as accurate. My recall might not be quite as good, but I can generally be 80% there. And then transfer learning is, I guess, probably maybe closer with. So the transfer learning is something very similar to that, where we take a known task and see how it transfers to a new task. So maybe we train a robot machine learning model to clean a dish, a plate, and then we ask it to clean a cup. How well does it do? Well, those are just some general terms I want you just in general to know. I put this in here about, kind of what we might see as future steps for AI. I'm not going to go over these, but it's really interesting. Some people think AI might and might not do. One really, really big thing is explainable AI. Now, what do I mean by explainable AI? Okay, because if you go to school for 10 years, get a doctor's degree, or a medical doctor's degree, and a machine tells you something, you just don't care. You just don't. You want to know why it thinks that. How did it get to that conclusion? And that is explainable AI. I don't know if I can make this graphing. It should be kind of zoomed out, but the idea is that right now, machine learning, for the most part, just gives you an outcome. I don't know anything really about sports, but let's say the Raiders and 49ers are playing this weekend. Yeah, rodeo weekend, Thanksgiving. I know there's a lot of sports games on. So the Raiders and 49ers are playing this weekend. And I design a machine learning model that says, boom, 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 tell me who's going to win. And it says, hey, the Raiders are going to win. Okay. And that's what machine learning does right now. But if I want to know why it thinks the Raiders are going to win, most machine learning models can't do that. And don't you think that's important? I mean, if you're going to bet $10,000 on it, that's a lot of money. I would like to know why you think the Raiders are going to win this weekend over the San Francisco 49ers. Is it because the home stadium advantage? Is it because the quarterback has a bad knee? What made you get that decision machine that's going to tell me that the Raiders are going to win this weekend? Explain your thoughts. It may sound very easy, but it's not very easy. And we have the same problem in humans. A lot of times in humans, we can't explain our feelings, our emotions, or how we got to a conclusion. Now, one idea that I'm kind of indifferent about. I'm not really thrilled. I'm not really unthrilled. Okay, I just have another great video list too. I just thought of another picture I'm gonna add here. So let me pause and add that picture here. Okay, I just added the slide I want to show you the next slide. So anyways, reinforcement learning from human feedback. So that's a kind of a weird concept. But basically, it's we have the machine learn from when we say as humans, yes, that's good, or no, that's good, or no, that's not good, I guess. And we do this all the time in the real world in theory. So an example is tipping. If tipping was truly a good metric of performance, servers, waitresses, hairdressers, whoever received a tip would know, hey, if I did this, I get more of a tip. If I do that, I get less of a tip. So it's one of those things that we kind of hope that an AI can get better with our feedback. Now, I don't necessarily have a problem with that as a main idea. What I kind of have a problem with is when we have to pay to do that. I don't have to pay a company $10 and then they use my feedback for their profit. So anyway, so if I go to Midjourney and you guys can try Midjourney, I think the cheapest tier is $10. There's 100 other ones, and I'll give you some other examples. ChatGPT does this. The perfect song that everyone loves, Crowd Bloom. So somebody type this in, and this is the one thing. So if I like one of the images, I can hit like upscale 4, and it'll make this image a little bigger, and it gives me this image. So now the machine knows that this group of words is linked to something in this image. If I do that enough times, then I know that, you know, hey, maybe, without the word crowd, it's just a person listening to music. With a crowd or crowded, it puts more stuff in the background. So it learned what these words mean by having millions of feedback. I was getting ready for speaking at a medical conference, Nevada Academy of Family Physician. This was an example I showed. So right before, maybe like a day or two before my talk, provider or doctor put this in a very realistic cartoon style illustration of a medical procedure. The diagram should depict a URSL showing a kidney with a ureter, and a medical instrument should be clean, detailed, professional with a light blue background, labeling version 6. So me personally, I mean, kind of have an idea what the image should look like, but not at the medical level I should. And I don't think really the machine has a really good idea of what the image should look like. So when the provider that typed this in, typed that in, I'm sure they hit, one of these buttons, say, hey, I like number 4. Boom, I click number 4. Next, go to the next slide. And then now the machine knows that this group of words is associated with that image. And as more and more doctors ask for this, it will learn better what to create. Again, I don't necessarily have a problem with this in theory, but I don't like to pay Midjourney. And I was paying Midjourney like $50 a month, and basically I'm training their models for them. Another example is ChatGPT. I was asking ChatGPT something, how to install NSF server and NSF mount on one of my NASs or something, and it gave me 2 prompts. I said, "Hey, what one do you like better? Which response do you prefer, this one or this one?" As soon as I click on one, sorry, it basically takes that and says, "Here's a question. Here's a better response." It's a little more complicated than that, but I'm training ChatGPT on how to make better outputs. Here's kind of the overview. So we have an AI model, makes a prediction. That would be what response do you like better? How do I set up an NFS file server? I look at that file and I say, hey, I like this one. I don't like this one. It updates the model parameters for the next person, and it starts over and over again. So that's kind of what human learning from, reinforcement learning from human feedback is. It's a very, very important concept, and I think it's often overlooked. Skip this one. The chain of thought prompting, because it's hard to teach without going into the whole LLM. Um, so machine learning, and like us humans, if we ask one question, we might get the answer, but we might not be the answer we're looking for. You know, if I ask, "Hey, what do you want for dinner?" and you say, "I don't know," and then I just order something, we're all unhappy. So if I ask, "Hey, are you hungry? Yes or no?" Yes. Okay, then I know she's hungry. What do you want for dinner? I don't know. Okay. Does Chinese sound good? No. What about Thai food? Yes. Okay. What type of Thai food? Like American Thai food or traditional Thai food? So I could kind of chain a prompt and drill down to a better question. So if you guys have played with ChatGPT o1, it does something very similar to this. It goes through and breaks down the question you ask and tries to kind of like chain of thought prompt through how am I going to get to the answer, how am I going to verify the answer, and what could be some other issues. So chain of thought prompting, the user's query is followed by a series of logical steps or thoughts that lead to an answer. This is akin to showing your work in a math problem or by breaking down your reasoning in an essay question. The model is prompted in a way that it understands not just a question, but also follows a guide to follow a reasoning response to arrive at the answer. So this is very important too. Like I said, I think O1 kind of does something very similar to this, maybe a little more complex, but it really helps LLM to get to the solution that I want and not just one answer. There's a couple different there's probably hundreds of small ones. There's a couple of different types of major neural networks. The neurons, the brains, and machine learning. Okay. There's a convolutional neural network. I have another picture, but it's often used for pattern recognition. It's used for like, hey, this is a picture of a cat, this is a picture of a dog, an RNN, a recurrent neural network. It's used, we have to basically take data, kind of summarize it or do something with the data and, the data is sequential or linear over time. A couple of things work a little bit better. Again, now GANs are, I've talked a little bit about GANs. GANs were designed by Ivan Goodwill. And it's got to be one of my favorite use of neural networks. And it's kind of really hard to explain to you, Luciana. I have good graphs on it, including very good pictorials on it. But you're basically training two models to fight each other. Not like in a physical reality fight, but to compete against each other. One maybe is a generator and it generates something, and one's a discriminator and it says, hey, that's not good or that is good. And at first, you really think of it, and you're like, oh, this is kind of dumb. What's the purpose of this? Why do I need something else like that? Well, you can also break those apart and it'd be very, very useful. Um, but I mean, the old the old analogy often is, hey, I have a generator that's going to make a fake $100 bill. And then I have a secret source agent and a discriminator that knows what a real $100 bill looks like. So I take the GAN, the generator, and generate a $100 bill. And the Secret Service agent says, dude, well, that sucks. It's written in Crown. I know better. So then the generator said, okay, let me do it in pen. And then the Secret Service agent says, hey, there's a misspelling, like on most of my slides, in the United States of America. And then the generator says, okay, let me fix that. And they keep going back and forth millions of times, millions of times. So you get something that the generator is generating really, really authentic looking fake $100 bills. And the Secret Service agent's really having a hard time trying to discriminate between what's real and what's not real. So if I then break them apart and I want to just detect counterfeit bills, I can look at the discriminator and say, hey, look at all these bills. What one's fake? And it does a really good job. Um, Here's an example though. There's a GAN that I use that generates fake medical data. And it looks very real. I mean, it looks very, very real. The diseases, the notes, the doctors, the billing claims, you would be hard pressed to know the difference between that data and real data. Now, why? Because I can't do a demo using real patient data. You know, United Health Group would get sued. It'd be horrible. Everyone would be upset. If I can do a total demo using fake medical data, and it takes me, I don't know, 10 minutes to generate, there's somebody trained a really good model on that. Finally, the new kid on the block is Transformers. That was from just a recent paper, 2016, 17, from a team at Google. And Transformers, there are a couple different things that make Transformers special, but one of them is self-attention. It adds context to the word placement. It can be paralyzed, um, and a few other things. But that's really Transformers. Really, what made large language models ChatGPT popular and effective to work with. So here's a little bit about just big picture difference between a CNN image and pattern detection and RNN. Okay, so I take a picture and I can break it down to like RGB or ones and zeros or 1 and 256. Okay, and then I kind of do a transform function on it, and break it down more. Maybe look for a pattern. I do maybe a high filter pass, do something. Doesn't really matter what. And I break it down more, and then I went through one of those neural networks, and they can kind of tell me what's an image. And we do this hundreds of times. The recurrent neural network, here's a little better structure of it. And we have some type of input data, this. We do some type of hidden layer, some weights. We do it again and again and again until these really, do well. And it outputs a whole list of output layers. Sometimes we just kind of say, hey, pick the best output layer or pick the best output that you think it is. And so like I said, they're very different in terms of the way they do it. Let me see if I have another picture. So here you can see here. So we take all these. So we're getting different values. So that is right here. So I have an RNA. So here's the only reason I wanted this is this slide right here. But again, I'm not sure how much you really want to dig into the difference between CNN and RNN. It's just that, like I said, in their uses, the input, the size of the input and resulting output are fixed. Receives an image of a fixed size and outputs then an appropriate category along with a confidence level. Well, RNN, the size of the input and the resulting output vary, receiving different text and output translations. The resulting sentences or data can have more or fewer words. So just kind of, I don't know for you all. A little another picture of CNN. So yeah, how can I do? So okay, so Transformers. Um, Transformers did a couple things. They really, I don't want to standardize embedding, so that's not cool. But the term embedding basically just means a way to convert something to a standardized format. Okay, so think of an embedding as converting medical terms, Parkinson's disease, into a standardized code. I don't know, PD40 that a computer system can easily interpret. Okay, positional encoding, like annotating a patient's records with a timestamp so that the sequence of events is clear. And that is important because in past NLPs, we can always understand the logical operation from one to another to another. So positional encoding tells us, hey, this word, uh, what's that saying? Let's go eat dinner, Grandma, or let's go eat Grandma for dinner. Something about that where there's a comma. Let's go eat Grandma. Let's go eat, comma, Grandma. The comma provides a very important um, semantic meaning. The first sentence, let's go eat Grandma, literally means that you're going to go and eat grandmother, cannibalism. The second sentence, let's go eat, comma, grandmother, means that, hey, let's go eat, and you're waiting for grandmother to join you, or there's a pause there. So that comma is important in that sentence. Additional coding. Attention mechanism. Now, attention mechanism, doctors might focus on certain symptoms when diagnosing a patient, giving more importance to clinical and less to minor ones or critical ones. And this is what I said earlier when I said that it has contextual awareness. Okay. I guess you can kind of maybe call it self-attention. So this is really what made that, plus you could paralyze it pretty easily. That's what, because again, you can paralyze it because you have embeddings. This is what made Transformers so popular. There's one other thing too. So I guess I should have a whole slide on the whole thing. If we have a brain like we do, and we want to change the output, if we have an LLM and we want to change the output, well, inherently there's three things we can do. We can change the input. So that's a RAG, retrieval augmented generation. So that's at the bottom. So basically, what a RAG does is we augment, and that's like Google Notebooks, for example, a really easy one to y'all to use. But we change the input, we give it an input more information to get a better output. In real life, in college, it's a cheat sheet. You know, with a cheat sheet, you still have to be able to read English. Still have to be able to read the question. You still have to be able to do all this stuff. But a cheat sheet might provide a little bit more information, a little boost to get you to the question. So RAG or inputting additional data or the input stage of a machine learning process, or a model. If we can augment that input process with a RAG, well, then we're giving it a little bit more fine-tuned information, note card, cheat sheet, whatever you want to call them. That's one way that we can change the output of a model. We can fine-tune it. What is fine-tuning, Richard? Well, fine-tuning is we take a model and we kind of try to change it. We try to revise it. We try to either edit that last couple of output rows or, yeah, I guess it makes sense. The last couple of output vectors, trying to make this as simple as possible. And so basically, we're not trying to change everything. We're just trying to change a little bit of it. Now, let's think about it. What's that like in college? That is college. We take everything you know from high school, and we're not trying to change everything. We're not trying to teach you another language, as your base language. We're not trying to teach a whole new system of math. We're trying to just augment, add, or fine tune their knowledge. Okay, here's the best way to do X, Y, and Z. Here's the best way to do math. You already know how to do math. You already know how to drive. You already know how to write a paragraph. What we're trying to do now is just kind of change the major parts to smooth them out to do what I want. So that's fine tuning. Finally, there's LoRa, there we go, low rank adaptation. Oh, I can never remember that. And basically, what it does is say, hey, well, we have a method we can change the front. We have a method that can change the whole, I guess, top of it. Well, what about the ass end of it, the output? Well, that's where LoRa comes in. LoRa is a method where we can kind of say, hey, here's normally the way it works. Input pre-trained weights, and we get outputs. But what if we took those inputs and we kind of modified the math on them a little bit? And we just changed them a little bit to give us the output we want. That's kind of what LoRa is. I think LoRa is going to become more important in a lot of AI processes. So in my graduate classes, to make my graduate students suffer, I give a 2-hour lecture on ethics, because data ethics and machine learning ethics, it will affect you. It will be your life. it will be your life. It will be an important thing that you will have to deal with moving forward. So I unfortunately can't spend 2 hours on ethics here. I think I only have two slides. Yep. But so let's talk about what data do we have the right to use? How do we know we have a right to use data? If a person's dead, how do we get informed consent? I mean, those are all just very basic questions. When you're here's another one. I read that Google can't use YouTube to do training videos for like making AI videos, but other companies can. Because when you signed up for YouTube, YouTube said, "Hey, we will not use your data for I don't know, improving Google or improving YouTube or something like this." But that doesn't mean other companies can't. Another thing is, should we tell people when they're dealing with a machine learning model that I think it was the one where we talked about the online forums and the chatbot. Well, people tend to like to talk to chatbots more so than providers, doctors, unless they know they're talking to an LLM or a chatbot. Then they don't like it as much. So should we disclose that they're talking to an LLM, or should we not disclose? Well, we've said this before that the learning large language models, so the ChatGPTs, guess what? It's trained on the internet. I don't know if you've been on the internet lately. It's a pretty dicey world on the internet. There's a lot of weird things, a lot of hate speech, a lot of racism, a lot of wonderful things, a lot of great books. There's also a large amount of bias out there, a large amount of false information. So how do we identify that and mitigate it? Um, what happens if a doctor and AI get in a pissing contest? The doctor wants to do one thing, the AI wants to do another thing. The AI has a good reason to do it. The doctor has a good reason to do his thing. The doctor is maybe 80% right. The AI is 95% right. Is it the doctor's choice? Is it the patient's choice who to trust? I mean, these are just some of the things that we really have to think about. Here's an important one. When we talk about ethics, as self-fulfilling prophecy, and this has been covered in a lot of books. So let's say the police force gets this new, really fancy AI model, this crime prediction model called Richard Young. And what Richard Young does is he says, "Hey, next week because of the weather, I expect more crimes in zip code 89123. I don't know if that's a real zip code, but I expect more crimes in 89123. So let's send more cops out that way." Guess what happens? More cops, they're going to automatically see more crimes. I mean, even if just the cops are pulling people over for parking tickets or speeding, since there's more cops, there's going to be more crime. It's a self-fulfilling prophecy. And this often happens in AI models. They predict something, so people do something, and it comes true. But that doesn't really mean that there are more crimes in that area. It just means that there's more cops that observe more crimes. And so, how do we prevent that? Bias and data we talked about with the internet. Yeah, the marginalized communities might be unfairly targeted, leading to cycle mistrust. Black box of unknown. So ML models, it's really hard to have it explain what it's thinking. Those are all ethical problems. So I got one more. No, okay. So I got like one or two more slides, and we'll wrap this up. So it's not about AI versus MD. So it's not about AI versus you. You have to really think about AI as a tool, AI as a way to augment. So do you think that linear regression didn't happen before Excel? That averages didn't happen? That a lot of things that we do did not happen before Excel? No, they happened. They were just not as fast. And when you learn Excel or when you learn Tableau, everything happened, most things happened before Tableau was invented. It just wasn't as efficient. So you have to think of Tableau as your partner, as a tool, as something. It's not like Tableau's going to take over your job. It's not like you're going to take over Tableau's job. It's a synergy between the two. AI can do some things very, very well and some things very, very poorly. I didn't include the slide, but AI is very, very good at detecting cancer or spots on a radiological exam. But it's very, very poor at writing radiological reports. So, very interesting. AI can mean anything. It's a very clicky buzzword, AI, machine learning, blah, blah. It's a very clicky word, so just be careful. We don't know what we don't know. And there's that saying that we have the known and the known knowns, the known unknowns, the unknown knowns, and the unknown unknowns. What's the unknown unknowns are really dangerous because we just don't know what we don't know. So that's where a lot of this comes in. We just don't know what we don't know until we kind of step into it. There's big money. Trillions of dollars are going to AI. And innovation, what's the downstream effect mean? So, if we add AI to Excel, how's it going to help us? How's it going to hurt us? And that's just one, downstream effect, and it just keep adding up like that. And remember too, I always like putting this one in there because right now empathy can't be replaced, and humans like empathy. If you were told that you have a cancer diagnosis, or that you have 6 months to live, or you have some type of chronic disease that's incurable, do you really want like a computer? Hello, Mr. John. You have 6 months to live. Thank you. Have a good day. The Richard Corporation proudly supports you. No, you don't want that. You want a human that tells you, I'm sorry, blah, blah. There's a lot that AI can't do. Maybe AI can take some of the burden off other tasks so that providers, we as humans, can spend more time on building that connection. Okay, if you guys want to take a screenshot of this, or what, you got the PowerPoints, but well, let me take that out. I don't know why that's in there. Yeah, I just copied the slide and didn't look at the bottom now. So there's a couple things I want you to play with. I guess it's the other Notebook LM. Notebook LM is a really quick, useful way to take a bunch of documents and ask that document questions. It's a way to interact with that question or with those documents or that book. ChatGPT and Claude. I hope all of you had at least a little bit of opportunity to play with some type of ChatGPT, Claude, Gemini, some type of model. And then once you do, you need to be thinking about, hey, why am I not asking it more questions? Which I know sounds crazy. I don't want you to ask it too many questions that are like not inappropriate. Hey, how do I become a better kisser? Useless shit. But no, hey, I'm trying to clean up my diet. Here's the last 4 meals I have. What can you recommend? I heard this vitamin is really good for me. How much should I take? What are 10 tips to avoid F1 traffic in Las Vegas? Can you explain to me the rodeo team bull roping and how it's scored? Can you explain to me why we have electoral college? Just think about all the things you can ask it instead of asking somebody else. Maybe you get a better answer, maybe you don't, but maybe you do. So Perplexity is just an AI powered search engine. Now Google is trying to do this, and ChatGPT is kind of doing this. So I don't know how useful this is. Some people love it, some people hate it, but just keep that in mind. And then now we have Apple Intelligence and Windows Copilot. If you haven't used Copilot, it's pretty nice. I use it at work a lot. I use ChatGPT and Copilot a lot. Apple Intelligence I use on my phone, and I'm on a Mac right now. So I use Apple Intelligence all the time, and they're both really nice. But more importantly, instead of having a ChatGPT that is isolated from your life, it's isolated from you. What is Copilot and Apple Intelligence? Apple Intelligence and Copilot, more or less, is integrated into your life. It's integrated into your email. It's integrated into your text message. It's integrated into your Apple Notes. So it's much closer at understanding you and fulfilling your requests. So I think that's the end. If you guys have questions, I'd love to talk about AI. We'll see if I can come up with a couple demos later this week for maybe ChatGPT. I have a couple demos I did for the neuroscience students, I think last year, and they're like 2 or 3 minute demos. I'll see if I can find them, maybe put those up. but it shows you how to take a screenshot of a picture and answer a question. It shows you how to summarize like a PDF. It shows you how to interact with the GPT better. So thank you.